Today's video is going to be about the inversion number of transpositions. Remember that an inversion number is just the number of places where we have numbers in the wrong order, pairs of numbers in the wrong order on the bottom row. The easiest thing to do is to first of all start off with a specific example, such as alpha is equal to, say, 2 goes to 5 in S6. So in two-row notation, alpha would look like the top row would be 1, 2, 3, 4, 5, 6, and the bottom row would be 1, 3, 4, and 6 are all just staying to themselves, and 2 goes to 5, and 5 goes to 2. And I'm highlighting the numbers that move in red for a reason, because I want to be able to understand how to quickly figure out the number of transpositions. And we're going to look at this example, and then we're going to wind up proving something in terms of a particular theorem. And if we're looking at this particular example, what I want to notice is that when we have that first number, everything up to and including the second red number, these are all inversions. In this particular case, the inversions would be 5, 3, 5, 4, and 5, 2. But we also have another set of inversions. And so let me get a different highlighting color. Let's do this. And if I look at this set of numbers, we get a couple more of inversions, and the inversions there are going to be 3, 2, 4, 2. And so every single inversion in this particular transposition involves things that are between the two red numbers. And that's worth noting over here. So all the inversions involve, in fact, they all involve one red number and one number between the two red numbers. And so if we just take a quick count in this particular thing, what we find out is that the inversion number here is, let's just do this real quick, 1, 2, 3, 4, 5. So we wind up getting 5. Well, the other thing that I want to notice before going on, and we'll make this note down here, 5 just happens to be equal to twice 5 minus 2 minus 1. In other words, 5 is equal to twice 3 minus 1. That's 6 minus 1. And where this 5 minus 2 is coming from is that that's basically the distance between these two things. You hop 1, 2, 3. And that's a pattern that we're going to investigate more carefully. So what we're now going to do is we're going to basically think in terms of any transposition. So we're now going to let alpha be A goes to B, where A is known to be less than B. And we're going to let alpha be in any permutation group, so I don't know exactly how big the A and the B are. Well, I can still deal with looking at the two-row notation for alpha. The two-row notation for alpha is still going to start with 1, and it's going to go all the way up to A minus 1, and then we're going to have A, and then we're going to have A plus 1, and all the way up to B minus 1. That's make that more readable. B minus 1, and then we're going to have the B, and then we're going to have B plus 1, and it continues all the way up until we wind up getting in. And of course, all of the blue numbers get sent to themselves by this permutation because it only sends A to B and B to A. So we have this second row and the two missing numbers is that A gets sent to B and B gets sent to A. And what I want to notice is that we can still look at the transpositions in basically the same kind of way as before. We are going to get a bunch of transpositions that start with B and end with the numbers A plus 1, A plus 2, all the way up to B minus 1 and A. So we first of all get inversions that look like B A plus 1, B A plus 2, all the way up to B minus 1, and then B A. And it turns out that if you start thinking about this, B himself is A plus B minus A. And so it turns out that there are B minus A numbers in this part of the second row. Well, what does that mean? Each one of those numbers corresponds to one of these inversions. And so that means we have B minus A inversions of this sort. Well, of course, that's not all of the inversions. So let's look at the other inversions. And what we have for the other inversions is going to look like this. We have inversions in this part of the second row that all end in the A, and they start with one of these numbers. So the other inversions that we have, we get an inversion list that looks like A plus 1, A plus 2, A. And this continues on until we get down to B minus 1A. It's important to realize that this inversion B in front of A was already counted over in our first list. Well, how many things are there in this particular list? Well, this list contains exactly one less of the inversions over here, and so it's going to contain B minus A minus 1 inversions. Now, what does this mean? Well, it means that we can add the two numbers of inversions together. So let's think about this. What we've got now is we have B minus A inversions on that first list, and the ones on that first list were BA, I'm going to circle them, BA plus 1, BA plus 2, that's messy, so let's do that again, BA plus 2, all the way up to B minus 1. And we have b minus a minus 1 more inversions that look like a plus. That look like a plus 1a, a plus 2a, all the way up to b minus 1a. So the total number of inversions inside our 2-cycle a comma b is b minus a plus b minus a minus 1. Well, we do some algebra and we get 2 times b minus a minus 1, and that is always going to be an odd number. So what this means is that every 2-cycle, every transposition is an odd permutation. Let's just abbreviate. Permutation. And that's actually an important idea, and we're going to highlight that because it turns out that this is a very important piece of sorting out how individual permutations can be broken down into products of transpositions. And let's see, that should say odd there. Okay, that will be enough for this particular video.